Alive. I don't know, we're alive. Let me get chat. Okay. I forgot to update the title. Say day 9. See if it updates. It doesn't. Weird. Page sine wave. What's it called? Output. Okay, does work. Why is YouTube chat so weird? Never mind. Okay. Yeah. So I have audio working, kinda. It blocks at the moment. So the options are either use the asynchronous API, well, that's the only option, I guess. Well, this. Yeah, I wonder if you can, if I could run it in a separate like separate thread. I have no idea how async works in Zig. Regressed with the release of that one. Multiple unsolved problems. Surmountable will take time. Okay. I think on one of the next releases. Alright, I'll think about it later. Yeah, I did see this. don't know. It's a bit of a detour, but let's have a look. News. Where's the... Oh, they have a new release. Or maybe not yet. Yeah. Or maybe yes. Seems like a sync is not the easiest thing to do. So, saw a video a few, I don't know, months ago maybe. Let's have a look at it. The new interface. The most notable change in SIG is that introduction of new interface in charge of all I/O operations. The I/O interface is now expected to be provided by the caller. It's like we already do with allocator. Okay. Create file. File dot write all data. Okay, that was the old one. And the new one. Standard.io. It's kind of like It looks like Go, but similar. The syntax. Is IO the interface? Okay. Okay, it's not too bad. I mean, I like the IO dot writer, reader, I don't know, one of those. Well, both actually in Go. They're pretty cool. Um, Makes it quite convenient to like write out to a file, HTTP response. Yeah, I do like that. Yeah, interface is also in charge of concurrency. An implication of this change is now that the author of the program is able to decide the concrete IO implementation. Okay, that's pretty cool. And I guess if you have your own types or methods, you can also just implement. Neat. It's also in charge of concurrency operation, as those can intertwine with IO, especially in the case of event loops. If a piece of code properly expresses concurrency of operations, then the IO implementation will have the opportunity of introducing parallelism. To show this example using to show this concept using an example, I need to write two different files. This is implementation that does not express concurrency and thus will not be able to leverage any potential parallelism offered by the IO implementation. Save file, AB. Interesting. IO.directory. Current working directory. The version instead properly encodes that there is no required order when writing two files. IO.async. Save file. Ah, interesting. This is the function, and that these are the parameters. My guess. It looks like it. A future, B future. A result is okay. You can await. Okay. and the save file looks the same. That's pretty neat. I do it, and as far as I remember, I think a sync is a break and change, or like whichever version this is released in. Using a wait on a function frame that hasn't completed yet results in safety checked legal behavior. And run over event IO implementation, but it'll correct when used with blocking IO, because IO sync will immediately call save file and future.await will become a no op. Where we had to use await. Where do they use try? Oh, okay, here. Oh yeah, interesting. Being able to do everything at once. The reason we can't immediately use try, because if we use try future.await were to trip, we could fail to await. Okay, interesting. Makes sense. Okay, got it. I said this is unfortunate user try is kind of our fault because we didn't go full length. Let's see what happens when we introduce support for cancellations. Oh, okay. Yep. See, so then you can clean up like edit differ. Switch it away to side. Additionally requesting cancellation from the IO. Cancelling are already implemented. IO operations return added or cancelled. Given that IO is an interface, you'll be able to create your own use and implement it in a third-party package. The most common one is maps to block in IO operations. All the implementation that include an event loop. String are all. Thread pool, green threads, stackless coroutine. I don't know what this means. Function coloring. Semantic I/O operations. The new writer interface features two new primitives for expressing operations in an optimized manner. A small subset of these changes will be present in ZIG 0.15. Have to wait until subsequent release cycle. Needs to be written and redesigned. Yeah, I did understand that from the video. Independent focus was saves progress faster. Alright, sounds good. Okay, I think I can start now. That was a small sidetrack.
Go ahead and start the actual recording here. Okay, hello everyone, and welcome to the Thanksgiving Day stream of Handmade Hero. I am feeling a little bit better today, I'm pleased to report. I'm hoping that I am actually starting to recover from my illness. Not entirely yet, that's true, but we're getting a little better. So I'm hoping that maybe pretty soon here I will actually be able to stream to you completely illness-free, maybe next week, who knows. Anyway, we are going to be doing our finishing up our sound programming today, just taking a look at the sound output code that we made and basically trying to go in there and inspect it and make sure that we don't have bugs in there. So the sound output code is kind of finicky. Direct sound's a bit finicky, the way that you actually have to use it, and so we want to kind of go through that and just shore it up, make sure that everything is working properly. And then after that, if we get done with that, we'll be looking at timers. So if you're following along today and you've pre-ordered the source, pre-ordered the game and want to follow along with the source code, you're going to want to go and get the 007 zip. That is yesterday's source code, and you can follow along with us on the stream by using that source code here on day 8. Okay, so basically we're just going to jump right back to where we were yesterday. I've got a couple of cleanup things I wanted to talk about that don't have anything to do with audio, but we'll get to them later if we get to them. They're kind of on my notebook of just things to talk about that I didn't get to yesterday when I was talking about, because we went right up to the end with sound. So, here we go. Here we go. Basically, yesterday what we did is we learned how to basically lock our direct sound buffer, which basically asks direct sound to allow us to write into it, to update the contents of the sound that's being outputted by the sound card. And then what we did is we wrote square wave into it, and then we told direct sound to unlock that, basically saying we're done writing into it, you can continue playing now. Now the other thing we did right at the end of the stream in the Q&A, people were asking why there was a pause. We waited until we had actually filled the buffer once in order.
Hang on, I'm just gonna grab my notebook. BRB.
to play the sound. So that's why this thing down here was true, because before we were starting it, before we had actually filled it at all, which causes a delay and so on. And so basically what we were doing is make sure we had it filled, then we start kicking it off, and we go from there. So the thing that I want to do today, first of all, is a square wave is a rather harsh wave. And so it's a little bit harder to hear if there are bugs in the sound output. And one of the things, I'll tell you a little story here on the Thanksgiving stream. We are not particularly time constrained today, by the way, so we could go a little long if we wanted to. I'll try not to, but we could. So one of the things that's actually kind of weird about audio, and that you kind of have to you just have to take it on faith when I tell you this. If you haven't had this experience yourself, then it may sound a little hard to believe, but you're just going to have to trust me it's true, and I'll tell you a story. So a long time ago, I don't know how many years it was now, probably 8 years, something like this, quite some time ago, we used to do a thing called the Indie Game Jam. And the Indie Game Jam was actually the very first game jam that ever existed. It was a thing that a bunch of us started. The very first one was held, Chris Hecker and Sean Barrett actually organized it out of a barn in Oakland, California. And basically it was a long time ago, and a bunch of us were sort of emailing about how computers had just gotten fast enough to maybe, if we tried, they could maybe render, I think it was 10,000 or was it 100,000? It was either 10,000 or 100,000 sprites on the screen. Just sprites, like old school sprites. And so what we were talking about is, well, what kind of games could you make with 100,000 guys? And so out of that was born the idea of, why don't we just get all the game developers that we know, all of kind of the friendly game developers who were all kind of professional. Everyone was working on AAA games at that time. There was no such thing as an indie scene. I don't know when this was, 2000, 99, something like this. Probably 2000 or 2001, I would say. So basically, we got everyone together and we said, all right, let's see if everyone comes down for a long weekend, how many games we could make that just play with the idea of having 100,000 guys. And so I worked on the engine for that jam. I think I did like a couple things, like the camera code and the loader that loaded Doom WAD files. That's where we got the sprites from. And then like Sean Barrett did like the renderer for it and stuff that would actually try to push 100,000 guys at once and so on. And so that when everyone got there was basically this code that could go ahead and actually render 100,000 guys, and people could sort of make games with it. And that was the very first game jam that there ever was. And since then, there's been lots of that idea of having a game jam where everyone just kind of packs in and makes a bunch of games has kind of caught on. And there's been lots of game jams, but that was the first one I think that ever actually existed, a concept of a game jam. But anyway, a couple of years down the road, we had done multiple of these game jams, and we got to a particular one, in fact, the last one that was ever held, I believe it was the last one, I think it's the last one that was ever held, was an audio game jam. And the idea was games that use audio to basically to capture the gameplay. So the gameplay was going to be audio oriented. And the guy who was doing the engine for that one, because again, the pattern for the game jams following that first one was always we built an engine beforehand, so that's not part of the jam, so that everyone when they show up already has a code base and they're just writing the game piece on top of that, basically. So so people would volunteer to kind of work on the engine and that sort of stuff. So basically what happened is the person who was going to write the engine for that one was actually Ottman Binstock, who you may know now. He's like the chief architect at Oculus Rift. He used to work for Valve, and then he left to go do Oculus stuff at Oculus to do the 3D headsets. Anyway, he was writing the sound engine, and he was living in Japan at the time. And I had never been to Japan, and I had always wanted to go. So I went out to visit him shortly before the Indie Game Jam was supposed to be held. And so he was showing me at a cafe in Japan. I don't know what's going on because I can't really speak Japanese and all this stuff. I think it's awesome. I love Japan. It was like probably one of my favorite trips, if not my favorite trip of all time, going to Japan. So we're there. We're in a cafe in Japan, and basically we sit down. And of course, since we're in a cafe, the only way to listen to sound is on the headphones, right? That are plugged into Ottman's laptop, and he was just like showing me the engine. He's like, here's the stuff I built for the audio engine, got this, got that. And he has some pair of headphones that are like the standard $30 headphones, just random headphones that you might buy or that come with an iPod or something like that. an iPhone. And I've got actually, quite some time before, I had actually spent quite a bit of money. I had bought some professional grade headphones. When I was working on sound quite some time ago, I had actually asked some friends. I think it might have been John Blow who first recommended them to me. He basically said, you know, they're called Etymotics. They're a headphone company. They make these like, you know, headphones or whatever. They're really, really good, but they're expensive. So I had bought some and I had them, and they are really great. They're amazing headphones. I've had the same pair for like a decade now. And so he's like showing this to me, and he's like, okay, listen to this. And I plug my headphones into his, laptop jack. And I listen to it, and I go, Ottman, you've got a bug. Like you're not quite aligned right on the buffer or something. You've got a bug. I can hear it. I can hear there's a little click there. And he like plugs his in because he's got his headphones, and we unplug mine and plugs his. He's like, I don't know what you're talking about. This sounds right. So I'm like, okay, here you go. And I give him my headphones. He puts them in. He puts the thing into the jack. He listens for a couple seconds and goes, I gotta get a better set of headphones. The moral of this story is you would be surprised at exactly how much variance there is in the sound that comes out of both speakers and headphones when you plug them in. There are different kinds of effects that happen to the sound on the way out. When you plug in crappy headphones, crappy speakers, or even good speakers that are going through a system designed to make sound better or smoother or warmer or whatever you want to call it, there's a bunch of essentially filtering, there's a bunch of mutation to the sound that happens. And that mutation, while it may make the sound better, or it may make the sound worse, who knows, obscures the truth of what is actually getting put out of the line, put out the line by the computer. So if you have very subtle bugs that result in very subtle artifacts in the sound, it's entirely possible that your sound setup may not even allow you to hear them. That is how finicky this sort of stuff is. Small errors in how you fill the sound buffer, small gaps, small differences can produce frequencies that you can actually hear on, and artifacts you can actually hear on very, very good frequency response audio output, like, headphones, speakers, whatever, but that you actually can't hear on lower quality or smoothing stuff that sort of munges with the sound. And so one thing that's definitely true is that if you really, really want to know if you've got a sound bug, beyond being able to inspect the code and try to verify things as much as you can, but if you really want to debug sound code, strangely enough, you kind of got to invest in a pair of headphones that have really, really good, accurate frequency response, that really accurately reproduce sound, because you may miss the bugs entirely. Anyway, Ottman did fix the bug, so it was gone by the time of the jam, but only because of the Etymotic headphones, so you got to give them props for putting out a good product, I guess. Anyway, that's a little story for you at the beginning of this stream. Hope you all enjoyed it. I'm not much of a storyteller, so I'm sure it could have been done in a more exciting way, possibly with visuals, but what can I say? All right, so I'm going to go ahead and open up Emacs here, just so we have our source code at hand in the editor as well. And then I'm basically going to take a second to talk about and think about how I want to go about verifying that this code works. So we've got a lot of moving parts here. There's a lot of things that we have to think about. First of all, when we come through it the first time, we fill the entire buffer, basically to give it something to play. And then we're going to go ahead and kick that off. So that means as soon as we fill the buffer the first time through this, then we kick off the playing here. It starts playing the sound, which means that play cursor, the thing that we're chasing essentially, is going to start moving through the buffer. It's going to start moving through the buffer, and direct sound is going to be playing what's in that buffer as the play cursor moves. And basically our job then, because we filled the entire buffer, so basically our right position is back to 0, our job is basically to go look at where that play cursor went to, and then go ahead and fill up to there. Now there's some complexities in how we do this, obviously, and there's some things that I want to point out that maybe aren't quite right. I'll give you an example of something that we're doing here that may be wrong. And so maybe we start to clean this code up, we start to think about these cases, start to debug it and make sure what's going on. But like, it was kind of a little hacky, it's test code and that's fine, but we're trying to actually pull this out into something we're going to use. Eventually, we got to start thinking about these things. So one of the things that we're doing, for example, is we get the play cursor here. We take a look if the play cursor is equal to the byte to lock. We assume that we're basically starting out, everything's at 0, and we're just going to fill. Now, why might that be wrong, right? Well, one reason it might be wrong is because the byte to lock and the play cursor, well, we know what byte to lock will be after we're done. If we write the whole secondary buffer size, then byte to lock is basically going to be back at 0, right? Because it's going to advance one whole buffer size worth, but we're modding by the buffer size. So every time we advance it one whole buffer size, it's back to the exact same position it was where it started, which in this case would be 0. So if the play cursor has not moved, the next time we get back through this loop, if the play cursor is back where it was, we would refill the whole buffer again, which is totally wrong because the buffer hasn't actually been played. Does that make sense? And that could very legitimately happen depending on the system, because let's say that we are on a system whose play cursor reporting isn't particularly accurate. You have to remember the play cursor is basically an estimate of where the sound card is in terms of playing out the sound on the speakers in some sense, but we don't actually know how that's being computed. That has a lot to do with what the sound output chip is on your actual computer, what the drivers are doing, how frequently they update with direct sound, how direct sound and the kernel mixer decide how they're going to report those values, when they're going to report those values, when they're going to service those values. We have no idea what's going on here. And certainly in the old days, that play cursor used to actually be updated very infrequently, in fact. Nowadays, I suspect it's probably a lot more frequent, the updates that are coming through it, but it's worth remembering that it could actually happen, that doesn't actually advance. So that's kind of a bug waiting to happen, in my opinion. So this, we need a more accurate check than byte to lock equals play cursor. Basically, what we kind of want to do is maybe write something that's a little more intelligent and wants to see that play cursor advance a bit and know that it has actually been updated before we actually fill it again. Like one thing we could do trivially, perhaps, to increase the reliability of this code would be to check to make sure that in 2 times through the loop, we have seen a different play cursor. Like don't take any action until we actually see that play cursor move, because if the play cursor hasn't moved, then we are in a situation where we really don't know what's going on, and we probably shouldn't be touching the buffer. Excuse me. Still sick. Getting better, but still sick. It is true. Okay, so that's something that we need to take a look at, certainly. Something to think about. The other thing that I want to do, and the first thing that I think we're going to do here, is that a square wave is actually not a particularly good wave for hearing errors. And the reason it's a very harsh wave, you can actually just tell just by looking at the square wave, and for those of you who were here yesterday, you know what the square wave is, but I'll just bring it up again just to refresh your memory. A square wave is basically a completely harsh cut. It's full on, followed by full off, followed by full on, or I should say full positive, followed by full negative. And if you think about that, that basically introduces this really hard, it's very unnatural. That's not something that you're probably ever actually going to see in the real world, right? Sound is a lot smoother normally. And so that's just a bad thing to test against. We don't really know what that should sound like intuitively. We probably can't hear errors in it very well. So the first thing that I want to do, and I didn't do this originally because I didn't want to complicate the explanation by starting to talk about transcendentals and things like this, is we're going to actually switch to a sine wave. A sine wave obviously is very familiar to most people, and you've probably seen it if you've ever taken high school math, at least in the United States. Typically everyone has to go through trigonometry, which means that you'll have seen something like a sine wave. A sine wave is basically a continuous periodic wave that just kind of loops up and down, very smooth, very continuous, and it sounds to your ear like a very pure tone. It is like the most pure sounding tone that you can really hear. It's like this perfect, smooth, no noise, no harshness to it. It's like a very warm, pure tone. And so what I'd like to do is basically just first switch over to a sine wave, because I think we'll have an easier time hearing the errors if we switch over to a sine wave for our sound output. So that's the first thing we're going to do. And in order to do that, we need to change the way that we're computing our sample value. Because remember, our sample value is currently being computed as a square wave. So we're going to go ahead and change this square wave period to just wave period, and a half square wave period to half wave period, because now we're going to actually not be talking about a square wave anymore. We are going to be talking about a sine wave. So if we actually go in here, the first thing that we have to understand is basically we're going to be seeing floating point numbers for the first time. And I'm not going to try to explain them fully here because we don't really need to understand them fully to do this. But there's something that's going to come up again in the stream actually fairly soon that we will have to start understanding in a little more detail. So this is just your first introduction to them. Don't worry about them too much, but try to start getting acquainted. Basically what I like to do, like everything else, is I like to have a type def for them because I like to be able to specify the size explicitly. Basically the types that I use for them are real 32 and real 64. Those are the two types that I use. And basically they correspond to the two built-in types for C and C++, which are float and double. Now a float is 32 bits wide and a double is 64 bits wide on the machines that we're talking about here. And basically that is usually true across a lot of platforms because there's a thing called the IEEE standard for floating point, and it actually specifies how the floats work and how they work in 32-bit. So you can actually take a look here. If you look this up, you can actually see there's a whole spec for these sorts of things that you can look at. It's not it's basically a very rigorously defined thing, I guess is how I would say it. So there's not a lot of flexibility across platforms with how the actual math works out when you're operating on these values. There actually is a very rigorous definition for how all the math has to be worked out. There's reasons behind all of it. We'll refer to some of it as we go through the stream, but a lot of the minutia here, there's a lot of minutia to floating point math that we'll probably never get to. Stuff that you only really care about in scientific computing or very delicate numerical algorithms where you care about stuff like, is something positive or negative zero? And yes, ladies and gentlemen, there is such a thing as positive or negative zero in the IEEE, and there's good reasons for it too, reasons that I don't necessarily pretend to understand very deeply, because some of the people who came up with this stuff were really crazy good at thinking about computer math and all of the ramifications of it for computing actual math. It's scary how much thought went into some of these things, and if you're into that sort of stuff, I highly recommend reading about the history of it and so on. It's actually very fascinating, but we're not going to go into that today or possibly ever. We're only going to kind of touch on them a little bit further out. So we are going to go ahead and include math.h, and this is just something, again, for test code. In the actual code that we actually write, we are probably going to take the time to not use the C runtime library for floating point operations that we're about to use the C runtime library for here. They're built in. Basically, if you want to call sine, if you want to call cosine, if you want to call tangent or anti-tangent, these sorts of things, they are actually built into the C runtime library, and sometimes they are built into the CPU. But some of them aren't built into the CPU, and one of the things that I kept harping on the stream over and over is that we're not going to use any libraries. And so even though some of these may be built in, some of them may not be built in, etc., what I want to do sort of in the stream proper after we get out of the platform layer is I want to actually show you how to implement some of these things yourself directly. So for at the moment, because we're focusing on sound, we're going to go ahead and allow ourselves to use that sine function for testing purposes, but when we actually go to implement the actual game, when we want to sine and a cosine, I'm going to show you a little bit more about how those things are computed and the things that we should actually be aware of to implement them ourselves. I think it'd be a good idea. I realize it's a little bit overkill. A lot of people watching the stream are probably like, that's ridiculous, but you know, like I said, we're trying to use no libraries, so we'll probably actually not use any libraries. But for test code, you're allowed to call anything you want if you want to. Test code is just basically about testing stuff as efficiently as possible. And so if you've got it, you can use it. That is totally fine. Much like here in the platform layer, we use all sorts of things like output debug string. When you're on a particular platform, always feel free to use whatever that platform gives you to get your test code up and running and that sort of stuff. That is always totally fine, obviously, as well. And in general, like I've said, sorry to harp on this, but using libraries and stuff is fine too. Some people have been getting the impression that I say don't ever use libraries or anything like that. That's not true. The only reason we're not using any libraries on this stream is just because I want to show you how everything's done, not because I think there's anything wrong with libraries. There are a couple libraries that I even like and I use. Sean Barrett's libraries, the STB libraries, I've used in code many times and I love them. So yeah, there's nothing wrong with libraries. It's just we're going to be trying to make sure that we really don't rely on any in our actual game code because I just want to show you how to build your own stuff. Okay, so we want to compute a sample value that's going to be a sine wave. So basically how this actually works is we're going to have one of our floating point values here that's going to be the sine value that comes back, right? We're going to have a sine value that's in floating point. The reason that we're going to do that is because all of these advanced math functions, the transcendental sine, cosine, tangent, those sorts of things, they do not operate on integers by default. Because all of these things, the mathematical definition for them is stuff like, sine returns a value between -1 and 1. That is just the mathematical definition typically of how sine works. You pass in an angle, right? If you remember your trigonometry, you pass in an angle. The angle is usually in radians, but you could also think of the angle as being in degrees and then convert to radians. Computers work in radians, but sometimes math classes teach things in degrees. So 6 and 1/2 dozen of the other, you can always convert between them. But point being, you pass in an angle in radians, and you get back from that a value between -1 and 1. So obviously an integer would not be a very useful thing to return this in because it only has -1, 0, and 1 as values, and you need all the values in between. You need all those fractional values. Now, one thing they could have done is decided to multiply it out so that it actually returned like -4 billion to +4 billion, or sorry, -2 billion to +2 billion as the values, and then, blah, blah, blah. But because if you're using sine and cosine, you're almost always dealing with very mathy code, and mathy code is almost always written in floating point. All of the math functions natively work in floating point as well. And we are mostly going to be doing our math in floating point too because modern processors have a lot of horsepower designed to facilitate floating point math, and we want to take advantage of that. It used to be, in the old days, in fact, when I was growing up, my favorite computer to program on. Again, this is a very meandering stream today. That's by design. I apologize for boring people with my stories, but I'm going to tell them anyway. Sometimes it's the coffee. I had some coffee this morning. Makes me very loquacious, it's true. I think coffee has a similar effect to alcohol, perhaps, where you start to think your stories are really interesting, even though they're no more interesting than before you drank the coffee. But here's the thing. I used to have an Amiga computer. I've said this on the stream before, and I loved programming on that thing. But one of the interesting things about computers at that time, especially home computers at that time, they oftentimes didn't have any floating point operations in the actual hardware. The 68,000 CPU, which was what powered the original Amigas, Amiga 500, Amiga 2000, Amiga 1000, those did not have what's called a floating point unit, an FPU. They did not have one in there, and so they actually could not natively compute anything in floating point. All of their computations were done with integer, and if you wanted floating point operations, that meant it had to be implemented essentially using integer arithmetic that simulated the floating point math, which is obviously very expensive, much more expensive, because you're doing a lot of operations to simulate essentially one operation. You want to do a floating point multiply, you got to do a bunch of integer work to make that happen. You're basically doing what the CPU would be doing internally. So in the old days, people used what was called fixed point. And what fixed point is it's basically a way of dividing up your integer into pieces. And you know what? Because it sort of worked, and I'm not going to use the word so well, because so well would be kind of overstating the case, but because it worked at all, let's just use that phrase, because it worked at all for our audio the other day when I was drawing out to you what we were doing, I'm going to go ahead and go over here to the diagram and just kind of draw out for you what I mean so that it's a little clearer. So if you imagine, basically we've got, I like drawing these little hash marks with either side. As you know, everything can be that. This was a sound buffer yesterday. Today this is going to be a 32-bit integer, right? So basically what happens in a 32-bit integer, right, and you usually look at them, this is going to be the 31st bit up here, and this is going to be the 0th bit down here, right? That's where we're at. And we've got, we can basically chunk this up into even parts that are 8 bits each. This is byte 0, right? This is byte 1, byte 2, and byte 3, right? That's what we've got, basically. These are bytes here, each one's 8 bits. So if you take a look at this 32-bit integer, there's a number of ways that we could imagine that it was divided, right? What we've been doing so far is we've either been assuming that it's unsigned, which means that all of the bits just act together to give you one value. So there's the 0 bit, there's the 1 bit, there's the bit that if it is set, it equals 1, then the one that's equal 2, then 4, then 8, then 16, 32, 64, 128, 56, 512, et cetera, right? And you add all those up together, and that's your number. So if you have the bottom 3-bit set, you know that your actual value is the 1 plus the 2 plus the 4, right? We went over this in the intro to C-Stream. Hopefully everyone's familiar with the binary encoding there. That's how we've been doing it. And then sometimes we've used negative numbers, and negative numbers use what's called 2's complement, and that's basically where you have the high bit is set, you know it's a negative number, and then the rest of these are encoded in a way that basically makes so the math still works out for negatives. You interpret them slightly differently. We didn't actually talk about 2's complement on the stream. We should probably do a stream about that at some point, but it's not germane at the moment, so we're just going to skip that. Point being, that's all we've done, though, so far. Now, there's other things we could have done with our 32-bit integer. Let's say that we actually wanted to store some fractional precision here. Let's say that we wanted to do something like have a number, so we have a number, right, like we would in math, with a decimal point, and then a fractional part that comes after it, right? Well, one thing that we could do, if we wanted to do that, is we could imagine that we just separated up our bits into this part, right, and this part. So we could just arbitrarily say, okay, let's say the bottom 8 bits are the fraction, right? And then the top 24 bits are the number, right? So this is a number up here, this 24-bit number, which means it can be up to like 16 million, right? So we have 0 to 16 million in the top part. And then down here, we have 0 to 256. And so we just assume that we have, 255, I should say, right? So we just assume that we have whatever this number is in the top 24 bits, and then we have a fraction that is essentially whatever this number is. We'll call this number f, let's say, for fraction. We have f over 256. So our number is whatever our number is in the top 24 bits, it's this thing, plus whatever this thing was divided by 256. You see how we could encode it that way. And you can see how that'd be pretty easy to extract as well. If we wanted to just know what the top number is, we could just shift this down by 8, right? So the whole number, we'll call the entire number w, let's say. If the whole number was shifted down by 8 bits, it would knock out the fraction and leave us with just the actual number, so we know our whole number very quickly. That's called truncation. It gets rid of the fraction entirely, right? It just gives us back the number. We could also round the number if we wanted to. We could add, right, half of this. We could add 256 over 2, or whatever, right? Actually, it's actually technically 255 over 2, so it'd be 127, right? We could add 127 to the bottom, which would mean that if it was 128 or higher, right, it would wrap and add 1 into here. It would carry into there, right? And that would increment our whole number by 1. If it wasn't, if it was less than that, then it wouldn't carry. It would just stay in here when we did the add. We could do that add, then do the shift, which would have the effect of rounding, right? So truncation would be this. This is truncation right here, right? That's truncation. And rounding is just w plus the fraction total over 2. Then we shift it down by 8, right? Hopefully, this is not a complete explanation either. Hopefully that kind of makes some sense, right? Do you see how that could kind of work? And then we're basically doing a bunch of math on numbers that are encoded this way. There's some other stuff you have to do with multiplication. You have to worry about the shifting because you've got an extra decimal place and all this sort of stuff. I won't really cover that. But basically, this is called fixed point, right? Oops, fixed point. Fixed point math. And this was something that people did back in the day in order to avoid doing really expensive floating point math when they didn't have a floating point coprocessor. That is fixed point. That's how that works. It's called fixed point because you have set an arbitrary fixed place where the decimal occurs in your number. That is how it works. You can never have more than 256 levels of your fraction, no matter what the number is, and you can never have any more than 6 million here because you only had 24 bits. So wherever you pick, you could change that decision by moving this around, but whatever the line is that you pick to write your math at, You basically are fixing the amount of fraction versus the size of the number that you can have. Does that make sense? So what floating point is floating point is a more powerful representation that basically allows you more flexibility at the cost of having the precision of your operations vary depending on the values involved. And basically what it is it's a different way of dividing up those bits. So floating point works completely differently. It's actually completely different conceptually than fixed point, really. How it works is it's divided up in a way that looks sort of like this. We have a thing called the mantissa, which goes down here, and this is basically a number that tells us only a fraction of 1. So it's basically a number between 0 and 1. That is how that works essentially in here. I shouldn't say it, I'm not sure how to explain this well. It's not really a number between 0 and 1. It's basically a value. Here's how, you know what? Here's how I'll say it. This is much clearer to what it actually is. If you imagine a number that's like 1 point something, and there's a decimal out here, right? So we basically have 1 point, 2, 3, 5, 9, 4, 7, 8, 6, whatever, right? Some fraction out here. The mantissa is a bunch of bits that stores this. It's the part that stores the fraction. The 1 is not stored. It's just assumed to be there. So it's just the fractional part. That's the mantissa, a fraction of this 1, okay? So the mantissa is here, and then we have the exponent up here. This is an exponent. So basically this is, if you know like an exponent, if you have something like x to the 4th power, that is an exponent, right? It's something that raises something to the power of. So we have the exponent, and then we have the sign bit. The sign bit is either 0 or 1, depending if the thing is negative or positive, right? That's all that means. The exponent is a power of 2 that says how big this number is. So essentially, whatever this exponent is here, whatever this value is, it's basically saying if this is n, it's 2 to the n. That's what it is, right? And then this is the actual fractional value. What this allows you to do is it basically allows you to separate the degree of precision you have in specifying the number, which is always going to be however big the mantissa is, from the scale of the value, which is specified here in the exponent. So this tells you the magnitude of the number expressed as a power of 2, and this tells you the actual value of the number, which will become bigger or smaller depending on what this is. So if this is high, right? If the exponent is high, then basically the mantissa encodes a much lower amount of precision for the value, right? Because whatever the fraction is, however much precision the fraction has in here, you're basically moving it up to a place in the number based on this n, right? So let's say this n is like 50 or something like that. Then you're taking 2 to the 50th, right? That's a very high number, and you're multiplying this other value by that. So even if it had a lot of fractional bits, even though that fraction is very specific, it's moving up into the whole number part because of this giant multiplication. On the other hand, right, if this number is negative, right, because this exponent can be negative as well, right? If this number is negative, then you're moving it down. Because again, 2 to like the negative n, right, 2 to a negative number is basically creating the opposite. It's making fractional values. It's making, it's dividing out, because that's the way exponents work. Again, this is just, I'm assuming you basically know exponents here. So what you're doing with that exponent is you're sort of sliding this decimal point around. So what ends up happening with the floating point representation is you basically have a situation where you've got 1 point, 2, 3, 5, 9, 8, 4, 7, whatever. You've got some fractional value here, and you're taking the point with that exponent. This is specified in the mantissa, right? So this is just represented in the mantissa. You're taking this point and you're sliding it by that exponent however many places the exponent is. So if the exponent is negative, right, you're sliding it this way. You're making it more of a fraction. You're making it 0.00000001 or something, right? If the exponent is negative, this is a negative exponent. And if the exponent is positive, you're sliding it this way, right? So you're making it bigger. You're making it 1 million something blah blah blah, right, or whatever. And that's why it's called floating point, is because the decimal point essentially floats. It's no longer fixed. It's not fixed point anymore. It's floating point. And what that means is when you do math with floating point, you're basically always guaranteed the same amount of relative precision no matter what your values are, right? You're always essentially getting the same amount of significant figures, if you will, right? If you ever saw that term. You're sort of getting that sort of equivalent of scientific significant figures in some sense, where you're saying however many bits of mantissa the floating point format you're using happens to have. And again, you can there's 32-bit floating point, 64-bit floating point, so the size, the precision varies depending on how big the total thing was. Basically, you're getting a certain amount of significant figures, which depends on the mantissa size, a certain degree of scale possibilities, depending on how many bits are in the exponent, right? And then you can do math at any scale allowed by that exponent will have the same number of relative significant figures. So if it's a very high number, right? Let's say, you know, it's some, again, we have 2, 3, 5, 9, 8, 4, 7, whatever, and this is some really big number, right? It's some number that's huge like this. We're still getting the same number of significant figures, essentially, right, here, as we would if we encoded that in a different way that was very, very small, right? If we used a different exponent for it, right? Here's the same number, but we've slid it down quite a bit, right? We have the exact same number of significant figures no matter what the scale is. We're never getting any more than that. We don't, once we get up to the scale, we can't even encode what the values are that go all the way to the decimal point. There might be tons of zeros here, and we have no idea what they should have been because we can't encode that. And same as here, we can't know what any of these things are because we've pushed it down too far. But that's basically how that works, right? Now, again, I'm drawing this all in decimal. I'm writing 0.000 as if they're decimals, and then these are all decimal numbers, right? And that's not really the case because this is all binary. So really these would be things like 0.001010101, you know, that sort of stuff. But you get the idea. It works exactly the same. You're still moving a decimal point around that has to do with that. So hopefully that makes some sense.
Find that quite interesting, personally. Why is it so odd?
Oh, I'm sorry. I just checked the stream. I guess I'm talking too loudly today. I should quiet myself down, perhaps. Maybe I'm getting a little too coffeed up. I'm getting a little too caffeine-y, and I'm clipping. Sorry about that. I'll try to calm down, make a much calmer tone. Okay. So basically, that is basically the way that floating point works. And we'll talk about this a little bit more as we go, so I can kind of explain more what's going on with the floating point numbers and why you have to understand some of these things. Because obviously, this is all kind of minutia. The processor is doing it for you now. So basically, what we are able to do with modern processors that we couldn't do, say, on the Amiga, which didn't have an FPU, they actually later added one in the 68030. So if you bought like an Amiga 3000, which was a later version of the Amigas, they had FPUs that could do some floating point math. Nowadays, everything does floating point math. Your graphics card does floating point math, your CPU can do floating point math, and in fact, most of the computing horsepower in your computer is often dedicated to doing floating point math because floating point math is where most calculations happen now. Certainly all 3D graphics runs through floating point math. Almost every stage of the pipeline is very heavily floating point now. Certainly all scientific computing almost always uses floating point math, although there are certain cases where integer math gets used and so on. So floating point math is one of the most important features
Quite funny the way it's calmed down.
of a CPU now. Even though they couldn't do them in the old days, they now have tons of horsepower for it. So again, even though we're taking a very handmade approach to this, fixed point, even in that case, is a very bad idea because really what you want to be doing now, if you're trying to be efficient and trying to be down to the CPU level, is you want to be using floating point because that is where the horsepower exists at almost every level of computing now, is that floating point. We're going to encounter some problems on the Raspberry Pi, I think, because I know there's some delicacies with floating point there. So that'll be a bit of a battle, certainly. But for the most part, in any modern thing that you would ship a game on, there is a ton of floating point horsepower. Even mobile devices have a ton of floating point horsepower. All right. we're gonna end that there, close our MS Paint session, and we are gonna go back to creating our sine wave. Now a sine wave is obviously very simple. I showed you what it looked like. All we need to do to get our sine value is we just have to call sine, and we have to call it with where we were in the period of the sine function, basically. Now there's two versions of sine. I can show you what they are. There's sine and sine f. I'm hoping if I do sine f, it'll come up with both of them. Yeah, here we go. Here's in the MSDN documentation. So you can see here, here's the sine functions, right? There's basically a sine f, which takes a float and returns a float. Those are 32, that's a 32-bit sine. And then there's a double sine, which is a 64-bit version of the same thing. There's 64-bit floating point when you want more precision, and there's a 32-bit when you don't need as much. We will probably never really use 64-bit precision for most stuff in the game, but it's worth noting that it's there. It's slower, always, pretty much. It's very rare that you can do 64-bit floating point math as fast as you can do 32-bit floating point math. Usually that's true these days because basically of SIMD. We won't get into that too much, but basically you tend to be able to do twice as many floating point operations as you can double operations because of the way that the processors work nowadays. So it's usually best not to go double unless you really know you need that extra precision. And in this case, we definitely don't, and for most of the game, we aren't going to need it, so you probably want to stay away from that. So we're going to call sine f, and we basically need to know where we are. We basically are in some position in the sine wave, which typically in math is called t. Usually t is the value that's kind of the running time value for your sine. So we need to compute whatever that is. But once we get our sine value back, remember our sine value is going to be a number between -1 and 1. But we actually want a value that goes between tone volume and negative tone volume. So what we need to do is we basically need to cast to an int 16, but we first need to take our sine value and we need to multiply it by the volume so that it will take it from a -1 to 1 version of our sine value. And why is it doing that? My keyboard is overzealous today. I don't know why. That's very interesting. There we go, it's a little bit better. Okay, so basically what we're trying to do is basically just scale our sine wave from -1 to 1 up to the tone volume so that it can be mapped into the 16-bit space properly, if that makes sense. Okay, so basically what we want to do here is we want to say, okay, we're going to do that, we're going to let that go ahead and put that back into our sample value. We don't care about rounding at this point, so we're going to ignore it. We're not even going to talk about that at the moment. And basically, we don't need this anymore, which is our square wave generator. And we'll go ahead and copy this down here after we're done. We need to collapse these two loops eventually, as our to-do says. So basically, in our T, we know that we already have a running sample index, which just keeps going up and up and up. So that is essentially our T value. But if we were to use that as the T value, the period of sine, right, I believe is pi, right? Let's take a look here. So sine, if you take a look at the actual scale of this thing, you can see that the period, well, the half period is pi, right? So 1 cycle is pi, and 2 cycles is 2 pi. So our half period, I guess we don't have to care anymore about a half period. We can literally just go with our period now. Since our period is going to be 2 pi, right? Basically what we want to do is say, as this thing goes up to whatever the actual period was going to be, which we computed, right? Here's our wave period. And we don't actually need this value anymore. The half wave period just doesn't need to be used. So whatever our wave period is, basically we have to say the running sample index divided by the wave period, right, is going to map that into a number from 0 to 1. As we go through the wave, it'll be 0, 1, 2, 3, 4, just like we did before, the divide that tells us where we are in the period. But what we want to do here is we want to actually convert these to floating point first, so that now we actually have smooth values that run from 0 to 1 fractional as we go through. I may have to diagram this out for you. I realize this is a little complicated and we haven't done stuff like this before. So I'm going to actually, I'm going to do a to-do, draw this out for people so they can see it. And then we need to multiply by the period we actually wanted, which was 2 pi. Now, we don't actually have a value for pi yet, So the other thing we need to do is actually do a pound define for pi. So here is our pi 32. That's going to be some real 32 value. And basically what we need to do is get the digits of pi and put them in there. Now I don't know exactly how many digits we need for a floating point pi. I'm going to go ahead and see if that's enough. Let's see here. Why do I always reverse the order of things? Yeah, it doesn't matter, compiler always catches it, so it's good. So basically what we're doing here is we're just transforming the period of running sample index into the period of sine. We're calling sine, we're multiplying it by the tone volume, and that's our sample value. Should be pretty straightforward. I don't think there'll be too much confusion there. But again, finicky code. I make a lot of stupid errors when I write code like this, even when I'm not streaming. So we may have to do a little bit of debugging here. Everyone brace your ears. It is time to listen to our sound, which could be totally messed up. Let's see what it sounds like. Why am I not hearing anything? What did I do? Did I do something? Oh, yes. We forgot to actually increment our value. I should just leave that down there as we play with this. There we go. Let's see. There we go. So I can hear immediately a scratchiness in that, right? And that means, I mean, obviously we could have messed up our sine value, certainly, but assuming that that is actually, assuming that that scratchiness is actually in there without the fact that we've messed up the sine value, that is sort of revealing the fact that there is clearly a bug in our wave output, which is what I wanted to do, because I was pretty sure there was, but you know, I wanted to actually make sure that we knew that first. So now we can actually go about starting to debug this. The first thing to do is to verify that our sine wave makes some sense. Okay. So one thing we could actually do if we wanted to is actually draw the sine wave out on the screen, which is probably what I would do in a normal circumstance. And I'm not sure if I want to do it now only because we'll have to sort of explain a bunch of drawing things to get there. But the other thing that we can do is we can kind of look at this code inspection-wise. First of all, step through it once, make sure that we understand what's going on. The other thing we can do is not fill the buffer. So basically, we know we had a 1 second buffer. So the very first thing I'm going to do is just never fill it again. So basically what I'm going to do here is this sound is playing, this thing that says if not sound is playing. That sound is playing, I'm just going to use that as a latch to only update the buffer once. So basically what I'm going to do is here is say, instead of calling get current position, I'm going to say if the sound is not playing and you were able to get that cursor position, then go ahead and fill that buffer, right? So basically I'm just going to do this. So what you can hear now, at least I hope you can hear this, if you can hear it, we hear only one skip. Do you hear that? Solid tone and skip. And how far is it apart? 1 second? 1, 2, 3, 4, 5. You hear that? Right? So when you hear that, what we now know, what that has determined, right, is that we have a bug in how we fill the buffers where the sine lines up when we fill those buffers, right? We know that our sine wave is actually outputting correctly because our sine wave, when we listen to it, when we listen to the sine wave just filling the buffer once, it sounds like a pure tone correct, and the only time it has a skip is at the end of that 1 second buffer, which is where it should skip because we didn't do anything to make sure that the sine wave wraps properly from the end of the buffer to the beginning. So there's a hard gap there, right? So basically we've now determined rather definitively that at least our sine output, this code right here, is working properly. What's not working properly is either the way that these two things are gapped together, because remember we're only testing one path. In fact, we can sort of see that here. When we come through and do this the first time, right, when we get this back, our region, our two region sizes, let's take a look at those here. Region 1 size, region 2 size. You can see that because we're locking the whole buffer that first time through because it's not playing yet and we're just filling the whole thing up, you can see that we only do one region fill. So we're only doing this fill. So we could have a bug here as well. That's entirely on the table. We have not ruled that out. But we know that we either have a bug there or we have a bug in how this stuff is updating, because we're basically saying when we start to actually fill the buffer up incrementally afterwards, we're introducing a lot of skips that should not be there, right? Does that make sense? And so there's a bunch of things that could be wrong about that. One is that we could be doing this fill wrong. One is that we could be incrementing our sample index wrong, so that we're thinking we should be, the place that we're actually writing into is not the place that we should actually be according to where we are on the sine wave. There's a lot of things we could be doing wrong, and so now we have to kind of go figure out what those are. Okay. So, first thing we want to check is just let's go through the code and just verify that we actually think we know what's going on here. We know we have basically a buffer that's going to be 48,000 samples long, which is going to be 48,000 times 4 because in terms of bytes, right? That's the bytes per sample. So when we init dsound, we're expecting to pass 48,000 here and 48,000 times 4 here. So let's go ahead and just step in, and we'll kind of walk through the code. We'll sort of analyze it line by line and make sure that we understand what's going on. Oops, I had to actually start it running again. There we go. So when we pass it in here, let's take a look. That should be 48,000. I'm going to switch out a hexadecimal display here. Samples per second should be 48,000. It is. Secondary buffer size should be 4 times that. That looks about right. 4 times 48,000. Yep, that looks right. That's what we expect. So our buffer is 1 second long, and it's playing at 48 kilohertz, which is what we wanted. We come in here, we process our messages, and then we're going to go here to fill our buffer. The sound is not playing yet. We go in here to fill the buffer. Our running sample index should be 0, and it is. Our bytes per sample should be 4. Now why is this not parenthetical though? That bothers me a little bit, because that should be a parentheses right there, and that is not how I would normally write that code. So I messed that up because the operator precedence, to be honest with you, I don't even remember what the operator precedence is between these two operators. I would never leave that be. So let's double check our operator precedence there since it came up. Operator precedence C. And let's see if it's got it here. Where is the mod operator, people? Where is it? It's right there. So these are left to right. So in theory, that's not a bug. So it would have been operating properly, but I don't like that at all. I don't like to leave things like that to chance. I don't like to be the kind of person who just memorizes the operator precedence and always embeds that in the code. I think it's a lot easier for other people as well as yourself to read code that looks like that, so you know unequivocally that's what they meant, and there's no problem. Don't worry about the 5-minute warning today, people, because like I said, this was going to be a kind of meandering stream on a holiday. So we're going to go ahead and blow straight through that. There will be a Q&A. We will probably just take the whole Q&A, the whole 30 minutes normally for Q&A to finish what we were doing, just kind of get comfortable. And then we will have a Q&A after that as well. All right. So basically we've got the bytes to lock here. That looks like a correct computation to me. The byte to lock, rather. Basically what we're doing is we're saying whatever our sample index was times the number of bytes per sample modded by the entire buffer size should be where we are in the buffer. That seems like a solid computation to me. I feel like that is relatively straightforward. I'm going to go ahead and recompile that here, and then I am going to step back to here, and I am actually, you know what the other thing I'm going to do is I'm going to remove our check there so that we actually can step through twice, because what I'd like to do is I'd like to verify that this wraps around to 0 again the second time through. So the first time through, we compute that byte to lock and it's 0. The second time through, I would like to verify that it's 0 again, and it is, so that's good. That's what I wanted to see, and wanted to make sure that the sample index would go up by 48K, and it did, and that all looks roughly correct. Okay. So let's move on to thinking about something else. So I think that running sample index looks kind of okay to me so far. You never do know. If the byte to lock equals the play cursor, that should only happen that one time. At the moment, like I said, it's a little iffy. We've got the to-do in there, but I'm going to go ahead and try to verify that it only happens the one time. Oh, no. See, look at that. We've already found a problem. Why is that happening? Why is the play cursor and the byte to lock always the same? Oh, you know, oh, that's funny. That is very interesting. So I think basically what's happening is exactly what this to-do said would happen. Basically, we are writing up to the play cursor, and then we always find that the play cursor has not advanced by the time we get through the loop the second time. That is what's happening, I think. So really, we just have to make sure that the byte to lock is behind the play cursor always if it is not. So if it's above the play cursor, that's okay. That means the play cursor, we have sort of wrapped around it. But if we're equal to the play cursor, that's actually something that maybe we're going to have to start just not doing anything, because we're assuming that we've already caught up and we're fine. So really that should probably look like this. So we're going to do a little bit of a hack here. If sound is playing, if sound is not playing, we're going to do that. And I'm just going to double check what that sounds like real quick. Let's see here. Okay, so that already eliminated one of our problems. You can tell that it's very different already. We still got problems, but that was definitely wrong. So all right, so let's think about this for a second. So what we should probably do is start pulling this out into a little bit less hacky, a little bit more correct code, so that we can do stuff like fill our buffer, control how we're filling our buffer a little more explicitly, so we can call it in here. So let's go ahead. I'm just going to pull this out here. I'm going to make a little struct called struct 32 sound output, and I'm just going to wrap these values up in there. I'm going to pull them out of there so that we can have a little more granular control over what's going on. So all of these sound values that we had, they're all going to come out into here, right? And I'm going to actually have those defaults set outside. So here we go in some code. We got to set up our stuff here. So if we make a Win32 sound output, this is our sound output struct, we can go ahead and then set all the values to what we were setting them to, like this. Here we go. Set the wave period, set the bytes per sample, set the buffer size. There we go. And these guys now have to be based on this. There we go. So we're going to set all that stuff up. So that's good. And then we are going to go ahead and make this initialization code happen down there. So let's get rid of these because we can't actually do those. You can, funnily enough, you could actually leave those in, I think, now. I think they added, the C++ 11 standard added some abilities to specify default values like that. So you could have actually left that in there technically. So we're going to go ahead and move that down into here. So basically we're going to create one of these and we're going to fill it out like that. So that's good. We are going to now call Win32 init dsound with those values. So now we'll initialize them straight out of the sound output, and that's fine. And then what we'll do is we're going to make our buffer fill stuff. We're going to actually make that buffer fill stuff be something that we can call separately, and we can give it a little bit more of guidance about what we actually want to do. So this buffer fill stuff right here, basically this part right here, we are going to pull out into something that can kind of be called in different ways at different times so that we can be a little more explicit about it and see what's going on. So let's see, Win32 fill sound buffer like this. And that's going to take one of these sound outputs like that. There we go. And then it will take the two parameters that were passed here before, the byte to lock and the bytes to write. It'll basically pass those in here, right? See that? So we're basically just extracting that code out. Again, like I said, I'm a big fan of just pulling things out when you need them. Instead of trying to design stuff up front, you just see what the patterns are that emerge and then you pull out. It's a good way to keep yourself in a good state so that the code's always actually doing something useful and you're not wasting a lot of time with abstractions that don't actually do anything for you. So that's the way I like to do it. Always pull out, start with the code, pull it out. All right, so basically what we've got here is we've got a function now that'll do this fill for us, and we just need to basically reference the sound output for all the parameters that we used to use. So bytes per sample was one. We've got running sample index, that's one. We've got our wave period, that's one. Got our tone volume. That looks like about it. We've got that. We've got this. And we've got that. Okay, so that should basically give us what we had before. Let's go ahead and compile that, make sure that works. That missed a couple. There's one. There's another. And there we go. All right. So now down in here, what we need to do is we need to actually call this function, right? We need to actually call our fill function down in here. And we will do that. And there we go. Now we will call the sound output. With that, we will use our byte to lock and bytes to write. And now this should basically give us the same code with the same bug It's just all we did was pull it out into another function. That's the only thing that we've done so far. So there's our sound output. Let's take a compile here and just fix our compile errors. Sound output, oops, sound output. There we go. That and that. So let's go ahead and just get that indented properly. And last but not least, there we go. So this should give us the same exact thing we had before. Same bug, same everything. Yes, and that is exactly what we get. So that's fine. All right, so now what we can do is we can make this stuff a little bit cleaner. What we can do is we can say, all right, the first time through after we init, let's go ahead and do a little bit of a fill. So let's go down here and say, all right, we've got our Win32 fill sound buffer. Let's go ahead and fill the sound buffer at startup. And then we can also do our play at startup as well. So we can kick the sound buffer off right here. That gets rid of that sound is playing variable. That's gone. And we could just basically kick it off right here. So what we're going to do is we're going to fill our sound buffer. Excuse me. We're going to fill our sound buffer. And we're basically going to pass it the first byte. And we're going to pass it, I guess we'll just do, for the bytes to write, we'll do the entire secondary buffer size. So that'll fill the buffer like we said before. Now what should happen here, again, is we should basically get exactly the thing that we got before. Let's go ahead and do this. We should get the same exact bug that we got before. Ho-ho! Now we are back to a pure tone, ladies and gentlemen.
I don't know how
In
we
fact,
fixed
a
it.
perfectly pure tone. So basically that check there was bogus. Why was that the case? That's very interesting. Let's take a look. Oh, even better. That was just an uninitialized variable. That's all that was. That was our entirety of our bug. We forgot to do that. That was it. No other problem. That was the entirety of our sound output problem. Awesome. So basically the only problem is when we went ahead, we had our problem of not catching up to the play cursor, so we had to fix that. But when I did our test for that, we failed to actually initialize to 0. Again, one of the reasons to start pulling code out and start making things cleaner. Cleaner code has less stupid mistakes in it, right? And that's a very good way to kind of look at that. Maybe we should have actually just initialized to 0 here, but at the same time, that was actually a legitimate bug. One of the things that's interesting about that is I think maybe this might be a case where we want to start turning up our warning level as well. We should probably look at that. I'm going to write that down as maybe something to talk about next stream. Getting the warning level up to something proper, because the compiler should warn us about a lot of things. Not necessarily that one, but we're currently working without a lot of warnings turned on. And usually when I compile my code, I have a lot of warnings turned on. So something to think about. But anyway, point being, now all of our cases actually initialize the variable properly. And hey, what a surprise, our sound output works. Works perfectly. Sounds lovely, doesn't it?
It does.
Listen to that pure tone. Are you loving that?
Now I've got to do it myself.
Are you loving that? I'm loving that. But yeah, that's something that we want the compiler to catch for us. And so maybe, I don't know, I feel like we could still make this stream be limited to an hour because we've done what we wanted to do today, which is debug our sound output. That has worked. We're pretty happy about that. And one of the interesting things is if you look at the latency here, our latency is now going to be the entire buffer's worth, right? Our latency is going to be one whole buffer's worth of sound because we're always writing up to the play cursor. What we could do in the future, and what we probably will do, is write less into the buffer, right? Instead of we're now 1 full second latent, which would be very bad for a game because we're writing a full buffer's worth ahead of that play cursor. But what we could do is basically say, let's not do that. Let's write up to some place short of that, basically, right? Let's take a look at the play cursor. Let's move only a certain amount ahead of it, and let's write up to that. So we'll look at that a little bit later too, if that makes sense. When it comes time to actually play sound effects, that is something that we'll be looking at. So what we'll do here is we'll say to do, basically, we want to change this to using a lower latency offset from the play cursor when we actually start having sound effects, right? This sort of thing would be fine for music streaming because it's not particularly accurate in terms of latent, but basically what we want to do is change that before we get to sound effects. So I think we have actually accomplished what we wanted to do for the day. Even though it was a meandering stream, we actually did exactly what we wanted. So that's pretty exciting. The only thing I do want to note is to implement Sine ourselves, because that would be nice. If you notice, if we go ahead and remove math.h here, you will notice we get an undefined identifier error because there is no Sine f actually implemented. So what I'd like to do is eventually implement that ourselves. We can look to, if we go in here to the Sine code, where is it? Let's see here, fill buffer. If we go in here and take a look at what it does, we can step into the assembly language and actually take a look at what that's going to do. So if you take a look here, it literally does call a function called sinef, right? I don't know if you can see that there. Let's take a look here. I'll be a little bit more explicit. We just called that one. Let's go back around the loop. Where's our jump? Jump, people, jump. There it is. So we jump back to top of the loop. We come down here, and you can see we call into this sinef function. Here is the sinef function. Oh, well, no, it's asm, and I guess it's not going to show us the sinef function because we don't have the source. But we can look at the raw assembly for it. Let's take a look here. Doing a compare, doing a load, doing a bunch of testing, doing a bunch of mulls, blah, 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 blah. You can look at that. That's a pretty expensive Sine, actually, it looks like. I don't know if that's the most... We may want to... we may be able to implement a more efficient Sine because we know that we only care about certain things as well. So that's definitely something that we probably don't want to just leave to chance. So we will probably do something with that ourselves. All right. Anyway, I think that is basically all we wanted to get done today. We will do timers tomorrow, and then finally on next week we'll actually, I think we're in really good shape. Next week we should be out of Windows code. We still will probably do a little bit with file loading in the Windows code, and we'll be massaging the Windows platform layer a bit next week as we go through it. But I think that's it. Tomorrow we'll do timers, and then we are good to go. Ladies and gentlemen, we have been remarkably on time with this stream. The first day, not the first day, the second day, I think, was the only day we really didn't get to as much as we wanted to. This has been amazing. I don't know. Give yourselves a pat on the back for...
Alright, now, actually, I mean, there's a lot more I need to do. Because I took a bunch of shortcuts. But before I do that, see if I can... Where's my audio? Alright, here. Yeah, I made a small little method. So I just got to modify this. Wave position, period. Call this tone volume. Not sure if I need this anymore. It starts from 0, goes up, then down, and back to 0. Or maybe, what is period again? I guess we don't need the byte to anymore. because I think Sine does it automatically. Here it goes to 0, term volume equals standard math Sine. Ah, yeah. Calculate E. Times the arc of sine of x. Is that just regular sine? Floating point number, use the dedicated. Oh, nice. Might even use the hardware directly. Same as using built-in sine. Sine of value and returns a value. That's convenient. What is t supposed to be? That's the one thing I'm not sure of. Well, I know it needs to consider the period. And is it just period times volume? He is 516, 32. Hey, hey, Nanasai. I didn't see the message, sorry. Is it easier to learn than Rust or harder? I don't know. I've never written any Rust. Honestly, Rust looks a bit scary to me. I've never tried it. Hey, Frankenstein. I'm from India. Volume equals sine of something with position times period. No. With position. Stone volume. Not sure. Not sure. Yeah, just watch out for your ears. Did anything happen? I don't think so. No, okay. Oh, because I'm not playing the audio. Yeah, that could be a problem. Let me just run it early on. I'll just play once for now. PCM, PC. Where's PC defined? Compatible types, U32. Okay, fix that. Just make it 916. Although it might not fit. How do you find in when I want to play a sound? Sine wave with frequency F. Two pi F T. Goes from 0 to 1 by F. I think F in this case. Position divided. not sure. I'm just putting numbers together at this point. Oh, sorry. Should be in cost. Oh, and we'll just make it U32. It doesn't need to be negative anymore. Okay, that one's easy. Vector integer or vector found F32. You mean, what is the type? Have I got the types wrong? It is float. Oh, okay, because it should be. Is that a float cast? Sure. Okay, that is. What am I doing wrong? Oh no, that won't work either. Do that. Really? Okay, it returns type T. Why is division so difficult in Zig? It's float cast. Make it temp divided by. I just want to make it work for now. Oh, period. Okay, at least it should divide. Okay, I think I'm doing something wrong. Imposition, blah, blah, blah. Or what I can do is let's make all of these float. Tone volume. Not really a big fan of this, but we'll have to do it for now. No. That has to be an i16 because the sound buffer is 16-bit. That might not work. For fuck's sakes. That obviously won't work. I mean, it makes sense. The number's too big to be converted to an N16. How do you convert float to int? Probably because the ambiguous expression. What? 16. That won't work, will it? No. Oh, hang on. Yeah, that should work. Motherfucker. Surprised that I've not done any casts of floats so far. Okay, how do you convert cast float to int? Int from float. Okay, nothing played. Could be that the audio is too quiet. Okay, nothing. I remember 8. 8 wasn't too loud. Okay, no. So that's need VS Code. Mm. If position is 0, T is 0, volume is 1000, tone volume is 0. Okay. Um, What is period? 187. Okay, yeah. Why is it stepping into this? Yeah, this number's always going to be too small. I think this is no correct. So it goes 0. This is like the period, and then it goes back to 0. Position equal period. The position is 0. Is T just the wave position? Could be too loud. It's 1000, the volume. No, nothing. T is 0. Yep. Volume is 1000. Tone volume is 0. T is 1000. Tone volume is still 0. What is sine of T? Oh, shouldn't it be Wait. Radians per degree is pi divided by 180. Times that. Yeah, nothing. T0. Okay, now we get like a really small number. I think we don't need the volume here. Or maybe we do. I don't know. Okay, that number is way too small. I'm gonna make it a small number just in case. So, debug. Rise to T0. Sine of T is negative something. Really small. Yeah, the number's too small. Let me just check Casey's formula. Back.
All right. we're gonna end that there. Close our MS Paint session, and we are gonna go back to creating our sine wave. Now, a sine wave is obviously very simple. I showed you what it looked like. All we need to do to get our sine value is we just have to call sine, and we have to call it with where we were in the period of the sine function, basically. Now, there's two versions of sine. I can show you what they are. There's sine and sine f. I'm hoping if I do here's the sine functions, right? 32-bit floating point when you ever really it's true to that level in the sine wave, which typically in math is called t. Usually t is the compute, whatever that is. But once we get our sine value back, remember our sine value is going to be a number between -1. So what we need to do is we basically need to multiply it by the volume so that it will take it from a -1 to 1 version of our sine value. And why is it doing that? That's very interesting. Just scale our sine wave from -1 to 1 up to the tone volume so that it can be mapped into the 16-bit space properly, if that makes sense.
Okay, so that part is correct. Oh no, it's not. Should be times. Oh no. Oh, I was right. Yeah. So I got something right.
Okay. So to do that, ignore. We're not even going to talk, and we'll go ahead. Which just keeps going up and up and up. Bit of sine, right? I believe is sine that the and half period. We can literally just go with our period now. Since our period is going to be 2 pi, right? Basically, what we want to do is say, as this thing goes up to whatever the actual period was going to be, which we computed, right? Here's our wave period. Whatever our, and we don't actually need this value anymore. The half wave period just doesn't need to be used. So whatever our wave period is, basically we have to say the the running sample index divided by the wave period, right, is going to map that into a number from 0 to 1. You know, as we go through the wave, it'll be 0, 1, 2, 3, 4, just like we did before, the divide that tells us where we are in the period. But what we want to do here is we want to actually convert these to floating point first, so that now we actually have smooth values that run from 0 to 1 fractional as we go through. I may have to diagram this out for you. I realize this is a little complicated and we haven't done stuff like this before. So I'm going to actually, I'm going to do a to-do period we actually wanted, which was 2 pi. Now, we don't actually have...
Okay, it's 2 pi. I think I get it now. 2 times pi times wave position divided by period. I'm sure Zig will convert. Okay, no. For a second there I was like, okay, I got it. Turns out I haven't got it.
Have a value for pi yet. So the other thing we need to do is actually do a pound define.
Okay, let me just check the debugger. What is happening? Either my volume is too low. Oh no, restart. Okay, that's the first iteration. Rise 2, tone volume is way too small. is 0.03. Okay, that one's much better. Okay, now it's gone into 1. But it's like really small though. What's the biggest it goes to? Okay. So, okay, that's because the volume is really low. Let's put it over 100. Can I hear anything? Okay, it's fine. 100 is way too quiet. 1000. Hey, there we go. Replace. So if I make it 8000. Perfect. That works. I haven't done any math in a long time. I will clean this up a bit. Before I do that, can I make it longer? Some buffer size, sample rate times 2. Okay, it's 2 seconds right now. I still gotta fix the whole blocking thing. Nice. Okay. I still... Okay. Let me clean up. Okay, seems like I'm gonna have to leave it as is. Oh, it was because... And from float volume. Hmm. Okay, I'm just gonna leave it as is then. I'm gonna have to change it anyways. Because this operation blocks use a async instead. And in order to use the async one, do, 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 simple sync. Okay, so the simple one is the synchronous API, which is fine. It's gonna be a bit of work, but then I guess it's gonna have to be asynchronous because it can't block for 2 seconds while it plays audio. Alright, gotta do this. Don't want to do it today. Do it tomorrow. Okay, I'll call it a day there. That was pretty good. I have a feeling the asynchronous one is gonna be a bit of work. Because the simple one was way too simple. But it's gotta be done. Because I guess audio is the last Linux thing we need. The file stuff is actually quite easy on Linux. Okay, I'm gonna call it a day there. I shall. It's a bit loud. Yeah, I'll see you back here tomorrow. Hope you have a good weekend. And yeah, I guess that's it. See ya.